Recording in progress.
Good morning, everybody. We'll get started here in a couple minutes. Thanks for your patience. All right, everybody. Thanks for joining in this morning. I'm going to go ahead and share my screen. Please, somebody kindly unmute and let me know if you're seeing the screen.
Yes, ma'am.
Thank you very much. Okay. So let's jump right into today's material. Well, let me just say, before we jump into today's material, let me ask if there are any questions at this point. On Tuesday, we started looking at 1D motion, and we got as far as looking at. Oh, well, I think I covered my notes. If somebody refresh me, did we watch the actual video on the graphing videos? Anybody recall?
No, ma'am.
We didn't watch them. Okay, good. I think that's what my starting point is. I think I've covered my notes. But we did not get into the motion graph videos, nor did we look at the sample problems. So that's what I want to do today. So now, bear with me while I try to set this up and make sure that it's playing correctly. Get to where I can skip over that. Okay. And I have to make sure. Let me stop sharing just for a moment and make sure that I have. That I'm doing this sharing correctly. There we go. I was looking for where that button was at. Share my sound. Okay, so now I'm going to play this video and you tell me if you can hear it.
To the video lesson on physics motion.
Can you hear it?
Welcome to the video lesson on physics motion graphs. The objective of this lesson is to understand the relationships of distance time, velocity time, and acceleration time graphs, and to be able to sketch those graphs for almost all the major types of motions that we'll see in this course.
Okay, so there are some of these items that, you know, in this video that we will deal with in this course, but as with everything, there are some aspects of these videos that aren't relevant for us, and I'll try to highlight, you know, those things that what you don't have to worry about that part of it. And then I'm not going to do the entire video because there are even some types of graphs that we won't focus on here, right? So there are some types of graphs we won't focus on, and even for some, the ones that we do, there are some aspects that you don't have to worry about, and I'll try to pause it and let you know exactly, you know, what's what there, so that if you're following along, you want to go back and use this as a guide, you'll know what to focus on. Okay, so with that, let me
Let's start by taking a look at the types of graphs that we can draw and the information that we can get from them. We start with the distance or displacement or position, all the same thing with regards to the graphs. So distance, displacement, position versus time graphs. The symbol that we'll be using for distance, displacement, position is X, and the symbol that we'll use for time. So for us, the distance time graph will be an X versus T graph. What can we get from them? We can, of course, the easiest thing we can get is we can get the distance at any given time just by going down to the time axis, going up to the best fit line, and then over to the left, find out how far it's going, how far it's traveled at some given time. We can also get the average velocity from the slope of the straight line. These two keywords go together, average velocity and slope on a distance time graph. And we can also get the instantaneous velocity from the slope of the tangent line.
Okay, so he's talking about instantaneous velocity. If you recall, when I gave you some basic definitions, I mentioned that those instantaneous proper values would have to be given because we can't utilize calculus in this class to calculate the slope of the tangent line, right? So that's one aspect of the video that when we're dealing with distance that you don't have to focus on.
To the curve at that point. So if our best fit line is not a straight line and it's a curve instead, you can see how we can't get average velocity from that because the velocity is changing, but we would be able to use a tangent line and get the instantaneous velocity using the slope of the tangent, and I'll demonstrate that for you later. Our next type of graph is the velocity or speed, and the same symbol we use for that is V versus time graphs, again T, so a VT graph. And what can we get from those? The easiest, of course, again, velocity time graph is the velocity at any given time. Similarly, we get average acceleration from the slope of the straight line. And one thing that is commonly tested is finding the displacement of the object by finding the area between the line and the time axis.
Okay, I wouldn't require you to do that because depending, well, I don't assume that you know how to use a graph to find area, but you know, the slope of a straight line, you can definitely find that from the graph. But even then, I've not required that students calculate that kind of thing in here, but more to understand what the graph represents and what kind of information you can get from the graph. I just don't necessarily have you get it from the graph, but you should know what you can get. You just don't have to actually do it. Okay, so usually what I do is I'll give you a graph and I'll ask you, what is the moving object doing? But I won't, in this class, I don't actually have you make those graphs. Okay, does that make sense to you?
Yes, ma'am.
Yeah, so you need to know how to interpret a graph, but you don't have to make them in here. Now, and in a lab class, you do have to make graphs, but you're not necessarily doing it to describe a moving object. You're doing a graph in lab class to express your data. So it's different, okay?
Okay, they really like to test that one. Okay. Our last type of graph is the acceleration versus time graph. Our symbol for acceleration is A, and of course versus T. So these would be AT graphs. And what can we get from them? Only the acceleration at any given time. They are the most limited type of motion graph that we can get as far as the information we can attain from them. And again, I'll demonstrate this for you as we start to do the various graphs for all the types of motion. Let's move on to that, and let's take a look at what we're going to do for each of these motion scenarios or situations. We're going to draw the XT, VT, and AT graph, one right under the other, so that we have a good understanding of the differences between the graphs and what they communicate to us. So we're going to start with an object at rest. We're going to start easy and work our way towards the harder scenarios. So for an object at rest, if an object is just standing there, that means that its position wouldn't be changing. And as time goes forward, so you could pick any spot, and what this of course means is that the distance is not getting bigger or smaller as time progresses. Okay. Well, if an object is at rest, that means its velocity is 0, and where the time axis intersects here on the y-axis would be where where velocity is 0. So we would have a VT graph that has a horizontal straight line on the time axis. If there's no velocity, there's no acceleration, so it also has a 0 AT graph, a horizontal line on the time axis.
So do any of you have questions about this first set of graphs for an object that is at rest? Meaning what? It's not moving, right? So if it's not moving, then the first graph says the position is not changing. Well, that makes sense. If an object is stopped, its position is going to stay stationary. And likewise, if the object is at rest, the velocity is 0. It's not moving, so it has no velocity, nor does it have an acceleration. Does that make sense to everybody?
Yes, ma'am.
Okay, because you see, the kind of thing that I would do is to give you a set of graphs like that and ask you, what is the object doing? And then you tell me, okay? You show me. Well, put it this way. I would give you the graphs and ask you what the object is doing, and you would have to describe that for me, okay?
Okay. We now go to an object moving at constant velocity away. What does that mean? That means the velocity is constant, but the distance is increasing over time. So this, of course, would be a straight line, sloped upward. And this, if you take a look, the X numbers are getting bigger while time is moving in a positive direction. That's the only direction time can move. Okay, and the fact that the line is straight means that the rate of change of the displacement or distance is staying constant, and of course that means constant velocity. If that's true, then on our VT graph, we're going to have some non-zero velocity over that same time interval, and it should be obvious to us that that velocity remains constant. You notice here that this horizontal line is above the time axis. The slope of this line is positive up here on the XT graph, so our velocity is positive on our VT graph. We still are not accelerating. This object is not speeding up or slowing down, so its acceleration value is 0. So this would be a horizontal line on the time axis. Moving on.
Oh, let me just back up just a tad.
So its acceleration value is 0. So this would be a horizontal line on the time axis.
All right, so let's look at this second set of graphs, right? Notice in every case, we're looking at position in the versus time in the first graph, velocity versus time in the second graph, acceleration versus time in the third graph. Okay, and so in the second set of graphs, notice that our velocity is not 0, but it's constant. So the velocity, remember, velocity relates to what? The idea of the object's speed, right? So you could kind of think of it as the vehicle is on cruise control going in the same direction all the time. And so the velocity is constant. Well, if the velocity is constant, that means the distance has to change. Okay, you're moving, so your distance has to change. And in this particular case, the distance changes uniformly. Okay, and so if the distance is changing uniformly, that means our velocity is constant. Well, if your velocity is constant, you're on cruise control. So you're not speeding up or slowing down. You're not accelerating. Okay, does that second set of graphs make sense to you, or do you have a question? Okay, I see I have something in the chat. Let's see what I have. Okay, I'm sorry I didn't respond out to the chat, Nikki. I'm glad you made it. Are you able to see things okay? Just if you put yes or no in the chat, it'll be perfect. And by the way, you know, thank you very much. Yeah, so back to that. I just saw the chat bubble and wanted to respond. I don't like to leave people hanging, and maybe, you know, I was thinking maybe it could have been a question about the graphs here, but all right. So I'll ask once again, for an object that's moving at a constant velocity away, that term away is important, because remember, if we look at the starting point, remember, we always have to have a reference frame, or where we're starting from. That means the object is moving in the positive, moving away from its starting point. Okay, so its distance is getting more positive. All right, does this second set of graphs make sense to you?
Yes, ma'am.
All right, that's what I want to hear. Okay, let's look at the next group.
Moving on to our next scenario, object moving at constant velocity toward. Well, constant velocity means our line is going to be straight. Toward means that our x numbers, our distance numbers, are going to be decreasing. So this would be a straight line, negatively sloped, showing that our x value is decreasing as time is increasing. Straight line indicating to us that the rate of change of that distance is remaining constant, therefore constant velocity. Well, constant velocity again means that we're going to have a horizontal straight line. This time though, our horizontal straight line is below the time axis. The slope of this line is negative, indicating negative velocity, meaning that it's going toward. So the first lesson we pick up here on VT graphs is that when your line is above the time axis for a VT graph, that means the object is moving away from the point of origin. And when the line is below the VT graph, the object is moving toward the point of origin. Huge point for you to remember there. Our object is still not accelerating, so its A value is 0. So again, we have a horizontal line on the time axis at which A equals 0.
Okay, so this second set of graphs is still dealing with constant velocity. Remember, you're on cruise control, pointing in the same direction at all time. But in this particular instant, remember, with respect to our starting point, the object is coming back toward the starting point. Okay, if you want to think of it like that. Okay, if it's moving away from the starting point, then things are positive. But if it's moving back toward the starting point, notice in the first graph, the slope is negative. And notice in the VT graph that the velocity is constant, but negative. Okay, so it's important that you understand the difference between if the object is moving away from its starting point or toward the starting point. Because remember, all of these things are based on measurement. And in order to do that, you have to have a reference point. And so, that's how we know it's moving toward or away, because of where we choose our reference point. Okay. Make sense to you?
Yes, ma'am.
Okay. Look, let me say this. I know, the tendency is, I don't mandate that you put on cameras. I can see that there are 10 people in the webinar right now. And if I wanted to know who's there, I could do that as well. But the most important thing for me is if you are here and you are focused on this information, do you have questions? Because this is the time to get your confusions cleared up. Well, there's no penalty, because you can ask me all the questions you want with no penalty. If something's not clear, stop me and ask. Even if you're just a little bit unsure, I need to be hearing from you, because these are the kinds of things that you need to be able to do. Notice for these graphs, there's no numbers involved. You're not, having to calculate anything. You're just simply looking at the graph and telling me, what is the object doing? Okay, so I can't stress enough. The reason you need to understand this is because everything you do after this point dealing with motion relies on this foundation. Okay, and if your foundation's weak, you know what happens, right? You're on sinking sand, right? I need you to be, strong in your foundation as we move forward. So with that, before we go to this next set of graphs, what are your questions? All right. That just means, man, grading midterms is going to be easy for me, because everybody going to make A's.
Okay. Next, we go constant object moving at constant acceleration.
Now, this is an important set of graphs here, this constant acceleration, because if you recall on Tuesday, I introduced you to 5 equations, if you recall, 5 equations of motion, okay, where the object is moving with a constant acceleration. Those 5 equations relate to these next 2 sets of graphs that you're going to be looking at. So if you took those 5 equations that I covered on Tuesday and you graph them, you will get these next 2 sets of graphs. Okay.
Away, that means this object is speeding up, and if it's moving away from the point of origin, that the x numbers, the distance numbers, are getting larger. This will result in a curved line that looks something like that, and curved upward means that it's getting faster. I'll demonstrate why for you here in a second. And away indicated by the fact that the x numbers are getting bigger as time increases. Okay, now why is this a curved upward line like this and not a curved upward line like I just demonstrated with the pen. Okay? If we take our tangent line, which I'm going to grab a tangent line down here and bring it up. We start out at the beginning here. Tangent line being a line that touches the curve only in one spot. You can see that at this particular spot, the slope of this tangent line would be 0. So this object had started from rest. However, when we go here and we draw our tangent line, now we have a positive slope for that tangent line. What does that mean? Positive velocity means the object has gotten faster. When we move upwards and higher on the graph, what's happening to our tangent line? Our tangent line slope is getting steeper. That means the speed is increasing. That means our object is accelerating. If we were to do the other line, and we'll have that scenario later, you would see that the slope would be decreasing, showing that the velocity is decreasing. Okay? All right, object moving, constant acceleration away. So that is going to be a straight line on our velocity graph, positively sloped. And that would indicate to us, of course, that the velocity is increasing over at a constant rate, therefore constant acceleration. And as we reviewed earlier, it's above the t-axis, indicating to us that the object is moving away from the point of origin. Now we do have a non-zero a value, and because the slope of this line is positive, that would be positive acceleration. So whatever that acceleration would be the y-intercept for this line, okay, and a horizontal line above the t-axis because acceleration is positive.
Okay, so this set of graphs, if you're paying attention, notice this set of graphs is very different from, especially where the position is concerned, from the other graphs that you've looked at. Notice this position, x versus t, position versus time graph is curved. Now, anytime you look at a position versus time graph and it's curved, you automatically know the object is accelerating. And if the curve is upward, you know that the acceleration is constant but positive. Now, if the acceleration is constant, it means you're pressing the gas. You're getting faster. So that means your velocity has to be increasing. But because the acceleration is constant, your velocity increases uniformly. Okay? So you have to be able to distinguish what the different graphs are telling you about the motion of the object. If somebody presented me with these graphs and asked me what's the object doing, the first thing I would say is, oh, it's accelerating, and that acceleration is constant. And so I know my position versus time graph is going to be curved upward in this particular case. What are your questions about this next set of graphs dealing with constant acceleration for an object moving away? All right.
Going to our next scenario, object moving at constant acceleration toward. Okay. This, of course, means that the speed is increasing, but we're losing distance getting closer to the point of origin. Okay. So this line would look something like this. Slope downward. Try to draw a better curve than I can with my pen here on the screen. Okay. For the VT graph, sorry about that. For the VT graph, constant acceleration means we're going to have start from rest and get faster, so the V numbers have to be getting bigger, but we're moving toward the point of origin, so we're below the time axis. So our V number is getting bigger, but being below the line means our line is sloped downward like this. Notice that the V number is getting bigger, meaning constant acceleration, toward below the time axis. Here we have a negatively sloped line. The slope of this is the acceleration, of course. So our acceleration would be a straight horizontal line below the time axis. Okay? Now shifting back to our next scenario.
Okay, so this is the last scenario that you would have to deal with as far as the different types of graphs. Okay, so we started off, our object was at rest. Then our object moved with a constant velocity. And then finally, our object moved with a constant acceleration. Okay, so, you know, the motion got progressively a little bit more complicated, right? So for this last set of graphs with constant acceleration moving toward, remember toward means what? You're coming back toward your starting point in terms of your position. What are your questions?
So does that mean it's going backwards, or does it just mean it's like slowing down?
It's not slowing down, it's accelerating, right? That acceleration is constant, so it is not slowing down. Let me, so you have to, well, yeah, I understand what you're asking me now. Yes, because the acceleration is negative in this case, right? I think that's what the question you're asking me. Am I understanding
Yes.
that right? Yeah. Because the acceleration is negative in this case, you have to be thinking about what does a negative acceleration do for the object, right?
Yes.
Yeah. So that toward is the key. So if you want to say moving backwards, I understand that terminology. I think that's what, because it's you're returning toward your origin. So I don't know if the backwards just means coming back toward the origin. I don't want you to mistake this with the vehicle, for example, that the vehicle is backing up. Because you could be, you know,
Going back to like the point it started.
yeah. So that was why in the beginning I said we want to keep things fairly constant in terms of what the object is doing. In this particular case, if your acceleration is negative, hit the brakes and slow down, okay? And we'll keep it as simple as that. Does that make sense?
Yes, ma'am. Thank you.
All right, okay. So that is basically what I wanted to show you where the graphs are concerned. Let me stop the share for just a moment, close that out. And then now I will reshare my screen, just a regular class page. All right. So again, all of those videos are available right under the required readings viewings, along with all of the other stuff that I covered and that you have access to from the textbook and otherwise. So, you know, if you need to rewatch those videos, feel free. If you want to rewatch the videos with my commentary, then the recording will have that available to you. Okay. The other thing that I said that I wanted to get into was to look at some sample problems. And I don't believe we did that on Tuesday. Am I correct? We didn't work any problems on this stuff on Tuesday. I don't think I got that far. Am I right?
No, man, we didn't work any problems.
Okay, so now to work the problem, to work some sample problems with you, what I rely on, I told you before, is like these extra resources, and you can get to all of that stuff right in the announcements, but I don't make it live in the course because of the fact that it goes out to the Google Drive folder that I made available to you. They got a thing about that kind of stuff, right? But hey, this is some good stuff, and I'm not gonna just not share it with you, right? But I always put with the caveat, use this if you want to, okay? It's just an extra help. So you see there's a whole folder dealing with 1D motion. This particular screen looks at it looks like the units, like the unit for acceleration is meters per second squared. But sometimes in the student's mind, the question is, why is it meters per second squared, right? Well, if you think about it, to get acceleration, you have this velocity changing and you're dividing by time. And remember, this assumes that the time starts at 0, which we typically do, right? But you have to ask yourself, well, if you get acceleration by doing change in velocity per unit time, what units go with change in velocity? Well, meters per second is the unit for velocity. So I have meters per second here. All right. And then on the bottom, I have time. What unit goes with that? Seconds. Okay. And so now the question is, if I take this, what does it boil down to? Well, I have meters per second divided by seconds. So I just took that bottom seconds and made it into a fraction. Dividing by 1 doesn't change anything. It just gives me a good visual of what's happening with the units. I have meters per second on top for velocity and seconds on the bottom for time. But you know the rules for fractions. If you divide by a fraction, you multiply by its reciprocal, right? So that becomes meters per second times 1 over seconds, because I just took this on the bottom and flipped it over and multiplied instead, right? So that becomes meters on the top, and seconds times seconds gives me seconds squared. So that's how come the unit for acceleration in the SI system, we're dealing with the SI metric system, and the base, the base is there, meters per second squared, okay? So that's a good guide when you're problem solving. Are you getting the right unit for acceleration? Okay, I do this for you because that meters per second squared, students mess it up all the time. They'll tell me that the unit for acceleration is meters per second, which means fundamentally you don't understand the property, because meters per second is for velocity or speed. Okay. They'll tell me meters per second cubed, and I don't know what that is yet. Maybe I need to go back and do some more studying on physics, but meters per second cubed, I don't know what property that is. So you can see clearly, meters per second squared. I can't stress that enough. In fact, what I tell students is, at this point in the class, what you need to do to make yourself your own little, study aid or support or cheat sheet or whatever you want to call it, is to write down all the different properties that you've come across in this class so far, and write down the SI unit that goes along with it. Like I always tell students, get you a big index card and start writing down all the different properties, mass, time, acceleration, speed, distance, all of the different properties that you've come across so far, density, volume, and write down, the appropriate unit that goes along with it. That way, if you're solving a problem, you don't have to get bogged down in the units. You know what the unit should be. Okay. Sorry, y'all. I'm in my office, but the custodian lady is doing the vacuuming. Go figure. All right. Another nice screen that I have for you here looks at the connection between our horizontal motion with constant acceleration and free fall. Okay, this is a real good screen visual to help you process free fall. So what is it? Remember, free fall is vertical motion, up or down, under the control of gravity only. So if our object is moving up or down, that's vertical, and gravity is the only thing controlling it, no air resistance, then the object is considered to be in free fall. And if it's on planet Earth and it's free falling, it has a constant acceleration of 9.8 meters per second squared down. Okay. Notice I said the acceleration points down. I didn't say that the object can only move down. The object can move up or down, but it is always going to be accelerated down by the same amount, 9.8 meters per second squared. That's because it's free falling. There's nothing else to interfere with it except gravity. Okay. And so this answers the question. When you throw the ball up, it comes back down. Why? Because gravity is always accelerating it down. Gravity does not accelerate an object up, right? So you have to be mindful of that, because a lot of times students tell me that if the object is moving up, gravity must be accelerating it up. Absolutely not. Gravity is always accelerating the object down, but it can move up or down. That's important, okay? So that first pyramid, you know, I like to use my problem-solving pyramid, and you'll see that here shortly when we do some sample problems. I broke the equations of motion. If you remember, I gave you 5 equations. Well, I just took those equations and simplified it into this one pyramid here if it's dealing with constant acceleration. You see, on the top of the pyramid, I have the final velocity minus the starting velocity. That's my delta V, change in velocity, okay? Divided by the time, all right? Notice that if I take the VF minus VI divided by T, I can get A. How come? Because whatever you're solving for, that's what you cover up. Okay. Now, that first pyramid means that our object can accelerate, like if it's moving horizontally. Okay. So that's why I say general accelerated motion. If the object is moving in any kind of way where it's accelerating, you can use that first pyramid. Okay. And I typically tell students that first pyramid is for horizontal motion. Think of it that way. All right. What if we want to deal with vertical motion for free fall? Because that's our simplest case of vertical motion, free fall. That means the acceleration is constant, 9.8 meters per second squared down. So I just took that pyramid on the top, and all I did was, in the place of A, I put G. And remember, G is constant. So if G is constant, and it's free falling, you don't ever have to ask me, well, I don't know the acceleration. It's free falling. Yes, you do. It's given. It's a constant. It doesn't change. If it's free falling, 9.8 meters per second squared down. Okay. So I just took those 5 equations and I boiled it down to one pyramid. It's much easier to solve using the pyramid than those 5 free fall equations, right? Or the 5 general accelerated horizontal motion equations, right? Remember we said horizontal motion X, vertical motion Y. In the top, the object is moving horizontally, but getting faster or slowing down. On the bottom pyramid, the object is free falling, but getting faster or slowing down, but the acceleration is constant. Okay. In the top pyramid, the acceleration is constant, but the object is moving horizontally. On the bottom pyramid, the object is moving with a constant acceleration vertically, and that means our acceleration is fixed. Okay. Now, when an object is free falling, we have a couple of different scenarios that it could be dealing with. I could drop an object, and that's definitely free fall. I drop it, it's free falling because gravity only. Remember, we're not dealing with situations with air resistance. So if I drop it, it's free falling once it leaves my hand. The only difference is, in this particular case, since I dropped it, its starting velocity has to be 0. So V naught or VI equals 0. But gravity is still working. When I drop it, gravity takes over. And so the object is going to be accelerated 9.8 meters per second squared down. Okay. So free fall, constant acceleration under the influence of gravity, 9.8 meters per second squared. What if I take the object and I pitch it down or throw it up? I pitch it straight down or I throw it straight up. In that particular instance, students first want to talk about force. This is not about force at all. Because remember, we're doing kinematics. Kinematics, you don't care about force. All I know is I pitched it up or I pitched it down, describe the motion kinematically. Don't tell me about force. Well, if I pitch it down or throw it up, that means its starting velocity is not 0. But it's still accelerating 9.8 meters per second squared. Whether I pitch it down or throw it straight up, gravity's in charge. That object is always accelerating 9.8 meters per second squared down. Okay? I can't stress that enough because students automatically think if I pitch it down or throw it up, there's force involved, so it can't be free falling. Absolutely not. This is not about force. This is about acceleration. And that acceleration is constant. If I drop it, pitch it up or pitch it down, it's free falling. The acceleration is constant, 9.8 meters per second squared down. Notice nowhere in here did I say the velocity can't change. Nowhere in there did I say the time can't change. What I did say for free fall that can't change is the gravity on planet Earth. At least we better hope it doesn't. Okay. I know I probably said the same thing about 10, 15 times, maybe even more, but it's because I really need this free fall stuff to sink in for you. Okay. What questions do you have about how we take our general acceleration equation on the top and transform it so that we can use it for free fall?
You answered the question I had.
Oh, good, good, good. All right. So you have access to that, remember, in the extra notes that you can get through to right from the announcements. All right. So it put one in PDF and a picture form. I leave them both there because sometimes students have trouble with the one or the other. So you have access to the both of them for the picture that I drew on the board. Okay. This packet is very nice, this first one, because it goes into the definitions. If you ever want to look at the definitions, it goes into that whole thing of explaining speed. Notice the nice pyramid that we use for speed, distance, speed, and time. Oh, so, hey, here's another pyramid, right? We took those equations, those 5 equations, and we simplified them down to 2 pyramids. One that deals with distance, speed, and time, and the other that deals with acceleration, velocity, and time. Okay. So I really like this because I don't have to worry about equations. I just need to know if I need to multiply or divide. Okay. And I'll look into come back in this packet in just a moment. This last packet talks about free fall and gives you some nice examples. Okay. But I want to go into this packet again, and I want to look at the example problems that they have available here. Okay. See, I like this packet because it's a little bit, it simplifies things to a level that I expect from you to be able to deal with. Okay. And it's a, you know, I always tell folks, it's really a shame that I can't use these as my primary lecture notes because it's beautiful. That's why I keep giving them to you like under, you know, on the side, like here, this will really help you. But I can't put it in the class notes because they'll fuss at me. All right. But what I want to do now, and you know, for the next couple of screens, is look at a couple of sample problems so that you understand the kinds of things that you are expected to be able to do. I don't expect you to use those 5 equations in the notes. I expect you to know that those equations explain the motion of an object moving with constant acceleration. But when it comes time to problem solving, I only need you to be able to use the 2 pyramids that I'm going to show you. So the first one says, your neighbor skates at a speed of 4 meters per second. What does that mean when it says speed 4 meters per second? It means that this neighbor covers 4 meters every second. It says you can skate 100 meters in 20 seconds. Who skates faster? Well, I know my neighbor's speed, but the question is, what's my speed? Because if I'm going to answer the question, I need to know how fast I'm going. Okay. So 100 meters in 20 seconds. Let's go to the distance, speed, and time pyramid. Okay. So if I want speed, I have to cover that up, and it tells me take the distance and divide by the time. So 100 meters divided by 20 seconds, 5 meters per second. Yay. I'm going faster than a neighbor. They're covering 4 meters every second. I'm covering 5 meters every second. Okay. Does this sample problem make sense to you in terms of distance, speed, and time?
Yes, ma'am.
All right. I appreciate you being vocal this morning because I don't know if everybody's paying attention because I'm not getting much response other than from you. And that always bothers me because that means either they really understand it or they don't understand it at all and they've just tuned out. Either way, I need to be hearing from you. Okay. It says a roller coaster starts down a hill at 10 meters per second. 3 seconds later, its speed is 32 meters per second. What is the roller coaster's acceleration? In a nutshell, somebody tell me, what is this roller coaster doing?
Free falling.
It's not free falling, thank goodness.
It's accelerating.
It's accelerating. It's going down a hill faster and faster. Okay. We know it's not free falling because gravity is not involved in this. In fact, they asked me to find the acceleration. If it were free falling, I wouldn't have to find the acceleration. I would know it automatically. 9.8 meters per second squared down. So they wouldn't have to ask me to solve for the acceleration. I would already know it. Okay, so that's important. I really appreciate your willingness to say that, because that helps clear up a major, major issue that a lot of students have distinguishing, is it regular horizontal type motion or is it free fall? So I appreciate you saying that. I got a message here. I don't think the speakers works. I can only chat, but I'm here listening. So you can hear me, but you can't talk because you don't have a microphone. Right. But your posting in the chat is just as good. And if you have a question, please post it in the chat. Okay. Thank you very much, Nikki, for keeping in touch with me. All right. So
I have a question.
yes.
What did you say the numbers were for the free fall?
9.8 meters per second squared down. Remember, on planet Earth, that's your free fall value, right? You see that screen?
Yes, ma'am.
Okay. So see, that's good, because you have to be able to distinguish some things. When do I need to solve for acceleration, and when do I automatically know it? Well, if it's free falling, you automatically know it, but the roller coaster is not free falling in this case. All right, so now they want me to find the acceleration. So in my pyramid, I can't use distance, speed, and time pyramid, because that distance, speed, and time pyramid doesn't even have acceleration in it. So that's why I tell students, be sure you're choosing the right pyramid. You only got two choices. Well, three, right? Speed, distance, and time, velocity, acceleration, and time, or free fall. That's the only three choices you have. So in this particular case, since we want to find the acceleration, we cover it up in the pyramid. And now all I have to do is divide VF minus VI by T. Well, they gave me VF, says 32 meters per second. They gave me VI, 10 meters per second. And they gave me the time, 3 seconds. Okay. So in that situation, what I have to do is subtract VF minus VI. I get 22 meters per second, and I'm dividing that by T, 3 seconds. Remember, you have to do that parentheses stuff first, right? Order of operations. So I got 22 meters per second divided by 3 seconds. That gives me 7.3 meters per second. The 7.3 you can get from the calculator. The meters per second squared. Well, remember my old screen here. If you're finding acceleration, what should your unit be? Meters per second squared. Okay. So you see, in that instance, I don't have to go through all that unit business. I automatically know this object is accelerating meters per second squared. See, certain units go along with the certain properties. Okay. All right. I can have a lot of different units to express acceleration, kilometers per hour squared, feet per second squared. But if I say, here's the unit, it can only be acceleration. So a property can have lots of units, but a unit only goes with one property. And in this instance, meters per second squared, because I'm getting acceleration. Okay. What are your questions about this particular problem?
Just to confirm, the smiley face is G.
No, because G only goes for free fall. The smiley face is A.
Okay, so it would. Okay, thank you.
Right, because remember, if it was free falling, you wouldn't need to find the acceleration. You would already know it.
Correct.
Okay. Yes, I know that, this whole problem solving thing is sometimes a challenge to keep straight, but that's, I think, just in those few questions that I've had, I hope you recognize the importance of understanding the concept first. Because if you understand free fall, you know you don't ever need to solve for acceleration because it's given. But because this roller coaster is not free falling, we need to know the acceleration. Or we need to find it. Okay. Let's look at another example of using our distance, speed, and time pyramid. Okay. It says sound travels 330 meters per second. If a lightning bolt strikes the ground 1 kilometer away from you, how long will it take for you to hear it? Now, a common mistake that students make in this situation, as soon as they read how long, they say, oh, we're finding the distance. How long? Nope. Keep reading. How long will it take? That is language for time. It's like if somebody walked up to you and say, hey, how long will it take for me to walk from here to your house? They're asking you for time. They're not asking you how far it is to your house. They're asking you how long is it going to take to get there. So you have to slow down and read the question carefully, because a lot of students mess up this simple type of problem because they choose the right pyramid, but they're looking for the wrong thing with it. Okay, so you have to choose the correct pyramid, and then you have to use it correctly. All right. So in this particular case, they gave me a speed of 330 meters per second. They gave me the distance 1 kilometer. But notice here, they did a unit conversion. 1 kilometer equal 1,000 meters. Somebody kindly unmute and tell me, why do we need to convert the 1 kilometer to 1,000 meters? Why can't I just use one kilometer? Okay. How about noticing that the speed is 330 meters per second, not 330 kilometers per second. You have to have like units, right? You can't do it because the velocity is in meters per second. Correct, Nikki. That's, oh, Hosea. I saw it. Sorry. Okay. Yeah, Hosea says because the velocity is in meters per second. That's absolutely correct. So I need to convert my distance to meters so that I'm having like units. You know, I can't mix apples and oranges. Okay. So now I go to my distance, speed, and time pyramid. They have asked me to find the time because they asked me how long will it take. If I need to find the time, I have to take my distance divided by my speed. And I know that because distance is on the top of my pyramid, speed is on the bottom of my pyramid. Okay. So in that case, it means I need to take 1,000 meters and divide by 330 meters per second. Well, see, if I divide meters by meters per second, then my meters is going to cancel out and I will have seconds as my unit. The 1,000 divided by 330, you can put that in the calculator, 3.03, all right? But the unit part of it, a lot of times students would tell me the time is 3.03 meters squared per second. And I would ask the question, when did your clock start reading meters squared per second? Nobody has a clock that measures time meters squared per second. So you have to pay attention to that, right? The meters per second is being divided by, it's in the bottom, so the meters cancel out. and you're left with seconds. But if you're finding time, that has to be your unit, right? You can't be having anything else but seconds in this case. Does this problem make sense to you?
Yes, ma'am.
Thank you. All right. Last one. Oh, let's see. Got a chat there. Yes, ma'am. Thank you, Renee. Appreciate it. All right. How long will it take a car traveling 30 meters per second to come to a stop if its acceleration is -3 meters per second squared? Okay. So this is similar in concept to the graph that you saw where the acceleration was constant but negative. You recall that one? I believe I had a question about how do I interpret that. Notice in his language, he used the word toward. That was very specific because that tells me that in this particular instance, when it's moving toward, that is coming back toward the starting point. As you said before, going backwards. So it's moving backwards, and that's what makes its acceleration negative if it's going toward. But think about this question right here. Your car is traveling 30 meters per second, and you come to a stop. When you hit the brakes, your car does not go backwards, so you do not move toward, yet you slow down. Okay? See, that's why we have to be very careful of how we talk about this notion of acceleration. Remember, it could be positive or negative, but you really have to look at the context to determine what the object is doing. Okay? When an object is moving toward and the acceleration is negative, hey, the speed is still getting bigger. It's just getting bigger as the object moves toward its starting point. Here, the car doesn't turn around, doesn't go backwards because you hit the gas, hit the brakes. Let's hope not. If your car goes backwards when you hit the brakes, please go and take that one back and get you a different one, because your car is not working right if you hit the brakes and it backs up. Okay? So this car is slowing down and coming to a stop. That's what makes its acceleration negative in this case. Okay? All right. So now they want to know, how long will it take for this whole thing to happen? It's going 30 meters per second, slows down, comes to a stop. How long is that going to take? And this time they gave me the acceleration, -3 meters per second squared. Somebody tell me, why is this acceleration negative?
Because they're slowing down.
Because they're slowing down. That's right. That's right. Okay. So I hope I've clarified for you the difference between slowing down but maintaining your forward motion as you do so versus a negative acceleration where you're moving back toward where you started from. Okay. All right. So now we can go ahead and find this acceleration. Okay. And in my pyramid, oh, sorry, my bad. They gave me the acceleration. They're asking me to find the time here. How long will it take? Yeah, Xenon, you got to be careful that you pay attention to what you're being asked to find, right? So they're asking me to find T. So I cover up the T in my problem solving pyramid. And then that tells me to take my VF minus my VI and divide it by A. So my VF is my final velocity. my VI is my starting velocity, subtract those, and then divide by the acceleration that they gave me. Okay. So in this instance, my VF is 0. Wait a minute. Why is my VF 0?
Because it asks you when it stops.
Stop. That word right there tells me that stop tells me that the final velocity is going to be 0, right? That's important to be able to read that correctly, because they didn't come right out and say VF equals 0, but they said it comes to a stop. So I have to match that with my understanding of what stop means, huh? Stop means 0, nothing. All right. So let's take the numbers that I'm working with here and put them into my pyramid. So that becomes 0 meters per second minus 30 meters per second. Now here's the temptation that students have, to always want to put the big number in front, so that when you subtract, you get a positive value. That's not what this formula says. This formula says VF minus VI. VF is 0, VI is 30. Put them where they go. Okay. And in that case, when you subtract, you will get negative 30 meters per second on the top part of your fraction. And you're dividing by the negative 3 meters per second squared on the bottom of your fraction. Okay. So be careful with that. Don't transpose those just so you get a big number in front when you're subtracting. Otherwise, you will be getting a time that's negative. And as the guy said in the video, time is not going to be negative. That means we have figured out some way to go back and go back to the past. We don't have those stones like Thanos and can manipulate things that way, right? So time can't be negative. I always tell students, if you solve and T comes out negative, you got 2 options. Go back and check your math, or pray real hard, because we can have a really bad day on planet Earth. Okay. So negative 30 meters per second divided by negative 3 meters per second squared. Negative divided by negative gives me positive. And meters per second divided by meters per second squared. Well, you can think of it as you have a meters per second on top and you have a meters per second on bottom. When you cancel out that, the only thing you're left with is seconds, which is what you should be left with since you're finding time. Okay. What are questions about this last problem? Are there any questions in general before we close it down today?
No, ma'am.
Thank you.
No, ma'am.
All right. Well, I appreciate those of you who were kind enough to engage with me today, ask me questions, respond in the chat. If you're working this weekend and you have, any questions or confusions, please reach out to me. I'm available to answer your questions. Other than that, as soon as the recording is available, I will make it available to you in the announcements. All right. So I appreciate you coming by today and engaging with me. Y'all have a great Super Bowl Sunday.
Thank you.